Hello there! In the last lecture, we put time at the same level of space. We treated it like a coordinate where to put the events, and possibly a static coordinate. So we obtained a possibly static spacetime in which everything is simultaneous, exactly like in space, which is the eternalist interpretation of relativity. Today we are talking about what differentiates space and time. So we're going to talk causality and in mathematical terms about metric. So points in spacetime are events. Events are things which happen, like I do breakfast, you sleep. They are all things which happen and which we put in some location in spacetime, like here or there. But what we require to make physics intelligible is at least continuity, which means events change with continuity. So it's not that now I am here, I do breakfast, and one instant later I sleep. So it's not useful to do physics to make predictions. So the way we construct space-time is in such a way that it makes sense with measurements. So a measurement apparatus is something which information is stored, so you can do measurements. So let's say this is information, a flash of light, for example. It bounces in this box, which is the measurement apparatus. And not only it must be conserved, the information, but it must also grow, otherwise you can't take data, right? So the information must have a direction in which it is contained in the box, and it does not escape. In general, it creates an always more complex net inside the box, a net of information. So it's not very trivial how measurements are made, and we should skip that. When constructing spacetime, we will only assume there is a direction in which it makes sense taking information, and the opposite direction would be losing information. So what is this process of storing information? Basically that is time. So for example, you see the planets which orbit around the Earth, and also other planets. Okay, that's the geocentric system, which is useful as a clock, and the Sun, which orbits also around the Earth. And you notice that there are some sequences which repeat. You can say they repeat because you have stored in memory other moments. So for example, every 2 times the Sun revolves around the Earth, let's say every 20 times the Sun revolves around the Earth, a planet makes a full turn around the Earth. So this is only an example. These are not the actual numbers. But okay, you construct these relationships to construct clocks. For example, if you have a pendulum, you notice that the pendulum oscillates, let's say, 600 times a day, and you use this pendulum to measure the days. You notice that it's always the same number. Say you count the events. This is time. Time is the measure of time is counting the events and comparing to other counts of the events. So there are 6,000 oscillations in one day, say in one rotation of the Sun around the Earth. So let's say that for every 1,000 oscillations of the pendulum, you have 1 full rotation of the Sun and 2 full rotations of a particular star. You can graph these relations. These are linear relations if they are always maintained. So you can create a scale of time. You can measure time by the pendulum equivalently as measuring it with rotations of the Sun or rotations of the star. But why should all objects follow this straight path? For example, there can be one path where if you measure with the pendulum, they get curved. For example, they make a parabola or any kind of curve. They can have different relations. And so, which one is the best clock? The sun and the star are the best clocks for the pendulum because they are linear. There is a simple linear relation between the sun, the star, and the pendulum. But these objects are not good for the pendulum. It is not good to measure the time measured with the pendulum. But at the same time, why should the pendulum be considered a good clock? So why do we measure time with these things and not with these objects, with this strange planet or this other strange planet? Why do we choose a particular class of linear relations? Well, that's apparently because there are a lot of linear relations with the sun or a lot of stars. In astronomy, there are a lot of linear relations, a lot of cycles which end containing other cycles and so on. And also when you use a pendulum which resists the air friction for quite a long, there will be a linear relation every time with the pendulum and the rotation of the earth or of the sun or of the stars. So this made Newton think, for example, that there is an absolute time, so that this class of time is privileged. So the pendulum is said to oscillate uniformly with respect to time, and these are said to be not uniform with respect to time. But that is only because you defined as uniform this class which contains the pendulum, and any linear relation with respect to a uniform phenomena is that also uniform. And of course you can't simply rely on yourself to find an uniformity of time. For example, you start counting 1, 2, 3, 4 and so on, but who tells you that you're counting uniformly? So when we define, for example, uniform motion with constant velocity, it is constant with respect to these clocks and not with respect to these clocks. And that is very important because uniform velocity is a very important concept in Newtonian physics. So Newtonian physics is all founded only on a particular class of time. Someone who thought quite differently from Newton was sein Freund Leibniz. Leibniz thought that time and space should be kept as relative concepts. But at the time of Leibniz, there was no usefulness in adopting relativity of space-time in physics. So this idea got ignored in the field of physics mostly, and it found place only with the modern theory of space-time. In fact, Einstein used to call himself a Leibnizian because of his conception of relative space and time. So Leibniz had a much more modern view for which it made no sense to talk about space and time without the objects, without the relations of the objects, because space and time emerge as particular kinds of relations between the objects, and there is no absolute stage previous to the events. The events themselves define space-time. So Einstein was probably quite inspired by Leibniz, but we reconstruct his space-time in a much more straightforward way, following the ideas of his professor Minkowski. So we will construct Minkowski's space-time. But first, let's see what we want to do in mathematical terms. We want to find a way to count, to measure distances. So we want to find a metric. Metric in Euclidean space is quite intuitive. You can go from point A to point B in different ways, and some path will be longer than other paths, and you can quite visually tell which one is longer. For example, you can define a long path by measuring the length with infinitesimally straight segments and then count, and you will see that this path here is longer than this. Or for example, you could use a clock. So if you take more time here and less time here, this will be longer. You see that taking a clock and measuring the time taken to go from A to B does not necessarily correspond to a longer distance and a shorter distance in Euclidean space. For example, if here you take the train, maybe you get faster to B than taking and going on foot from A to B with this path. Also, if there is a gravitational field in the y-axis and you must go from A to B, this is the shortest path geometrically but not temporally, since you have the bakistochron at the shortest time path. Well, in spacetime we are going to do that. We are going to count length with clocks. So if you have a clock, you go somewhere in the universe and your clock made 2 ticks, you made a path of length 2. If it made 1 tick, you have a path of length 1. This is quite useful because this is a very intuitive notion of distance, which does not rely on something like a universal ruler or a universal clock, but only by counting the events of a particle you follow, only counting his own clocks. You just look at the events and count the events, but not the events of a particular clock which you take as a reference for that particle and maybe all the particles, but the very clock of that particle. What is a peculiarity of this metric? We have, for example, path of 0 length, because if you take, for example, a photon or a signal in general, signals don't change from one point to another one. That is why they are useful to send information. So there will be the path followed by signals which will be of 0 length, for example. So the clock of the signal does not tick. Why there should be clocks which tick slower than others? Well, because if you take, for example, a particle, you define a particle as a system which communicates constantly with itself, so it is, for example, kept together. You have that there are certain signals inside that particle which make the particle evolve, right? Because to change things in a particle, you need signal exchange. If signal stands still, then the whole object stands still. So if this is the signal inside the particle, but the particle is moving at the speed of the signal will never reach the particle. So the particle has no time. So time is an emerging property of things which move with respect to the signal. So how does a photon clock work in spacetime? You see often in textbooks, photon clock is simply represented by these 2 lines which will form the time axis. And here we have the photon which bounces back and forth to the 2 points, the two lines in spacetime. And this is a photon clock which defines the time axis. 1 bounce, 2 bounces, 3 bounces, but there is a problem here, that it does not explicitly show where the information is accumulated. There is a accumulation of information, there is a flux of information. It's this direction or this direction, because simply from this drawing there is no flux of information, so there is no counting of the photons, because every step, every part is exactly identical to the others, so you have no memory accumulated. So to actually draw a photon clock, you should add another wall, and here the photon splits into photons. One gets reflected and the other passes through, and so on. Also here, so here you have a photon trapped. Here you have two photons trapped, because there is also this photon here, and here you have three photons trapped. So you count the number of photons in your, so your memory is given by the number of photons. 1, 2, 3. So this way you can count the bounces. So you see that the clock is not symmetrical, because there is accumulation of information in this direction but not in this direction, and it's the flux of information which defines time. So I invented this photon clock just for this lecture to explain how it can work, but this can be summarized in fact in some ways. For example, this, you can draw an arrow in the travel of the photon to emphasize that the information is accumulating in this direction. Or you can also simplify it even more simply by drawing a line. You can, for example, think of it as an infinitesimally small clock, and you draw it only as a line and with an arrow, and then where the photon bounces you put the numbers 0, 1, 2, 3, so you count the number of the photons, and the numbers are growing, which means the information is accumulating in this direction. This is in fact the time axis. So when we draw a time axis, you should think of it as a simplification of this kind of structure. We will talk about space axis when we will talk about coordinates, but you can think already of a space axis as a clock where information is not accumulated. So when you draw the arrows, they go from here to here and from here to here, and there is no flux here, as you can see. The flux is only here and not inside the clock. So this will be a time axis, but this will be a spatial axis. So you can, here in this representation we have drawn the time axis perpendicular to the space axis. For example, the time axis is given by a clock like this, and the space axis by a clock like this, but we will talk about it in more detail in a few moments. So we will use clocks to construct our spacetime. When drawing spacetime, we must differentiate between two things. One thing is how spacetime is represented, it is drawn, which is basically arbitrary, and the other thing is the actual relation between the events. So let's start from a totally arbitrary clock. We only require continuity by now, which means that if we have our signal which propagates and bounces, we can follow the signal, and we will not have one part of the signal here, one part on another place very far away, but we have continuity, so we can follow the signal in space-time, in the space-time we are drawing. So this could be the signal and the path the signal makes, the bouncing between these two lines. So how we draw these lines is a priori completely arbitrary. They can be curved, so we will have a time axis, and we can think of the clock, of a single clock also with two time axes, right? Because when we had drawn the clock, we had two parts of the clock, but we could also think of this other part. Then we will make the two axes covered, but we will do this later. Now let's take them separately. So a photon bouncing represents two clocks. Our flux of information follows a particular direction, this particular direction. So we count the photons: 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on. This is a clock T prime, so it will be 0 prime, 1 prime, 2 prime, 2 prime, 4 prime, but it's not important the prime axis because it's just counting the photon. But we want to keep it just to emphasize that these are counted by the clock T prime and these are counted by the clock T. Then what we do is we represent these axes parallel. For simplicity, it's arbitrary. It's our choice. Our choice is to draw these axes parallel because it's more simple. By the way, remember that spacetime is 4-dimensional. Now I have drawn it 2-dimensional, but now I will draw it 3-dimensional so you can better understand how the photon can move, because the photon can actually go here and not necessarily in a plane. So here the photon can turn around and go here, then it can turn around, go here, and so on. Now we are simplifying the representation of the clock more and more from 1 to 2 to 3, and in 3 what we do is we want the photon to make a simple path, so we say that it is all in one plane. So here we have the two parallel T and T prime axis, and our photon makes his own path in this plane. It can be a curved path again, but it will be in one plane. So now we are drawing our photon only on the plane of the board. So now another thing is that here we can have drawn, for example, here the instant 1, here the second 0, sorry, here the second 1, and the second 2. They can be very far apart or very close to each other, but we want to relate the uniformity of the counting with the uniformity of the paper or the board. So we will draw different seconds at equal distances, just for simplicity of representation. So here we have our time axis, here our T prime axis, and here they will have the same distance. Also, this is something arbitrary, and it's only to simplify our representation, our intuition of the uniformity of counting. And so now number 5, we make the path of the photons equally, because remember that the photon is only needed to relate the events, but the line of the photon itself does not have a particular meaning. So if you take a point here, it does not have a particular meaning if we don't have a clock in between. So we draw it how we like, and we draw it such a way that they are all equals. Instead of doing here these and here these things, they do the same thing. Now the number 6 will be, the simplification number 6 will be that at this point we can do it in straight segments. Also to emphasize that there is no much difference in this clock and this clock. So with our convention number 6, we arrived to this kind of clock. It finally looks very nice to look at. We could use this drawing notation for an infinitesimally narrow clock, so that by continuity every other infinitesimally narrow clock in the neighborhood will be quite as simple as this, because if this is not an infinitesimally narrow clock, then here in between you can have other clocks where things are quite strange and it is difficult to use this notation conveniently. Instead, if you use this notation for a narrow clock, then you are defining a simple drawing notation for locality and for local physics. So you have here your clock, here neighborhood clock, where also the light will go in straight segments and so on. So the neighborhood would be basically the first term expansion of our spacetime. So the region we have drawn, which looks nice, is often called the flat region. And we have basically a flat spacetime where all the spacetime looks nice independently on the distance. But in a generalized curved spacetime, this can work only in the neighborhood of our clock. And the choice of the clock which looks nice is totally a convention. It is what we call a frame of reference. So notice that the pillars of our spacetime are the light path, because the light path relate the events. So spacetime is drawn starting from the light path. And this is a huge difference with Newton's spacetime, because in Newton's spacetime you draw the time axis, the time coordinate and the space coordinate, and from those you universalize them, and they coordinate a position in this axis determines the whole physics, the whole events. Instead, here it is not the coordinate time itself which defines the relation between all the events, but how the events are interconnected with light cones, how they interact between each other. So this is a far more concrete approach. In fact, this kind of approach can work in general. So when you draw spacetime, you basically draw the light path as straight segments by definition. We have seen that we can make a grid with these segments, right? This grid, if we take the projections, and also by taking all the infinitesimally close path of light. We must take infinite lines, infinite photons to draw a continuous spacetime. So this grid of photons defines the spacetime. And of course, in 2 dimensions it is a grid, but space is 4-dimensional. Now I can't draw 4 dimensions because it gets messy to represent, but I will draw it in 3-dimensional spacetime, and they are clearly light cones because you also have this dimensionality here outside the board. So you extend the grid to the 3rd dimension, and you have multiple cones of light, and these cones of light define your spacetime. Remember that geometrically these light paths represent path with 0 length. So an object, if this is a light grid, an object which goes from here to here by following this grid is a photon. It goes on path of 0 length. You also draw the clock, the infinitesimally narrow clock in 3 dimensions. You have t prime, and now you have a full cycle of parallel time axes, t second, and so on. And you can make these infinitesimally small and define a time axis, an individual time axis with this clock. So let's now look at the spacetime from the point of view of our clock. These are the path of light which defines the clock, 0, 1, 2, 3, 4, and so on. And now let's focus on the 0, on the light emitted from the point 0. So this will be the light emitted, because remember that we assume a flow of information, and this will be the light absorbed by this point. So we can do it in 3 dimensions. So here we have a cone of light, and also here, and we can communicate with a point inside the cone, for example like this, by sending signals, and a point here can communicate with 0 also by sending signals. So the point here send signal to 0, they can send signal to 0. The point here, a point to which 0 can send signals. So this is called the future cone, and this the past cone with respect to 0. And what about a point outside here? Can we send a signal to this point? Well, if we follow the light path, we would do something like this. But remember that the flow of information is going here. So for a sufficiently small region of spacetime, at least, by continuity, also here by continuity, because the flow can't change direction all of a sudden. So by continuity, here also the flux must be in this direction. So here also there is an arrow in this direction. So the arrowhead is not in this direction. So we cannot send a signal from here. But this can only send, this point A can only send signal to our cone. But we can't from this cone send signals to A. So when you start from 0, you can't send signals to any point here, and these points also cannot send signals to 0, because you can, for example, go here, but here the arrow here is pointing here, so you can't go here, you can't send a signal to 0 from here. So it's this flux of information which separates these 2 zones, or these 3 zones, the future light cone, the past light cones. All these events can be connected with 0. These events can't be connected with 0. Now, in the frame of t, let's compare our clock t to another clock t prime, which is an arrow in another direction. So this would be t prime, for example. Let's say this is the light cone, so this is a photon. Then our clock t is constructed like this. You take a parallel line, and you make the photon bounce, and you count the events. We do the same thing with t prime. We take a line parallel to t prime, and we make the photon bounce. So here in t, the photon bounces like this: 1 bounce, 2, and 3. Here in t prime, the photon bounces like this. So here we have 1 prime, and then the photon again goes here, it touches the other side, and so on, and the second 2 prime is very far away. Now I have drawn it again. The clock ticks here in the t clock, and the t prime clock, which is more slow. Now the important thing, which is the difference between the main difference between Einstein's physics and Newton's physics is that the pillars of spacetime here are not the coordinate axis, but, as I said before, the light path. So we have drawn the T frame of reference in such a way that we had this nice grid of photons between the two lines defining our T clock. And we could have done the exactly same thing with T prime, always by having this nice grid of photons, but now between the axis T prime. So when we draw the spacetime by T prime, now we have that these are the ticks in T prime. 1, 2, 3. Now T is to the left of T prime, so we will draw it here. And now we do the same reasonment that we did with T prime here. So we draw a parallel axis to T and we construct the T clock. We send a signal, this is the light cone, we send the signal and we send it back, and we have 1 second, and so on. So now by this frame of reference, it's the T clock which ticks more slowly. And all this is because it's the photon which makes the coordinate in Einstein's spacetime. There is no coordinate a priori. In Newton's spacetime, you would think something like this. You would think this is T, if this is T prime, and here the clock ticks more slowly, and here it ticks like this when I changed frame of reference, and here I have T prime, then here I should have T which ticks faster. This is a reasonment you would do in Newton's physics, because you start from the coordinate and you don't follow the light path. Instead, here you follow the light path to draw the clock. So when you pass to the frame of reference of T prime, now, since the light grid is drawn the same according to T prime, then it's the T clock which ticks more slowly. Now here we have compared a clock which was inside the light cone. Now what about a clock which is on the light cone? Well, that's very simple. If you try to construct this clock, you see that it does not tick because the light moves together with the clock. So as we said before, this does not measure any tick, so this is all zero length, so this can't be a clock. What about the clocks here? If you have a time axis here in this other region outside the cone, well, you see that to make a clock here the path of light go like this, but we have the flux of information which is sent here, and here, so here it is not sent here because the flux is going here, so it is sent here again. So we are sending information from here to here, from here to here, and there is not a flux of information through the clock. So this does not measure anything, so this is not a clock. So the clock can only be inside the light cone. So this region of the cone, this region is called the clock zone or the time zone. Instead, the region here is called space zone. The cone of light is simply called the light zone. Now, before going on, let's do some clarifications. The width of the clock T prime has no reason to be the same width of the clock T. Now, I have drawn it about the same width, but it has no reason to be the same width. In fact, the flux of information in this direction is different from the flux in this direction, while instead all the clocks parallel to t in a neighborhood of t must be drawn with the same width because we are using the same drawing convention. It's not clear how the width of t prime should be. And the width is determinant to know how time flows in t prime in the frame of t. For example, if we have a very narrow width, the bounces go like this, and this is faster, clocks faster according to t. But if the width is very large, then the bounces, like this, and it ticks very, very slower according to t. Also, let's clarify how t determines how time in t prime flows, because we haven't talked about the space dimension yet. You usually would think like this. You project the bounces of t prime in t, and you see that they are shorter. That is not what t sees. In fact, t sees only when the signal of the tick arrives. So you must project the signal of t prime in t to understand what t sees. In this case, you see that the signal of the first tick in t prime arrives before the tick in t, so t prime is faster here, while instead here the signal of the first tick arrives here, so t prime here is slower than t. So our spacetime is not fully determined yet, and to determine it, it is useful to consider also the directions with no accumulation of information. So we need to talk about the space coordinate. In Newton's physics, the space coordinate is quite straightforward to define, because you just take an instant of time, and if you take an instant of time, since the time is universal, you can take an instant of any clock, and then you can define the space for which you have instant 1 in all the space-time, and instant 2 in all the space-time, instant 3 in all the space-time. So these lines are the perpendicular spaces, the spaces where time is constant. You can do it in Newtonian physics because you don't follow the light path to determine where the positions of the seconds are in these clocks, but you follow only a projection of t, of your universal clock, of any clock. You can start the projection from here, or from here, and you determine the projection for the whole space-time. So you don't follow the photon, but you follow the time projection. You follow an abstract line. It's very abstract because this does not represent a photon like in Einstein's physics. This line is the line of simultaneity. So space in Newtonian physics means fixing one value of time and taking the whole space with that value of time. All the events in that space which have that very value of time are said to be simultaneous. The transformation from t to t prime here is quite simple. The space is measured with a ruler. So this is 1, this is 2, and so on. And the x-axis coincides in the two transformations. So the vector 1, 0, in this notation you have the first is the time component, the second is the space component, so this is the vector 1, 0, and it goes to this vector here, rotated by an angle alpha, and this length here is the tangent of alpha, so it goes to 1 minus tangent of alpha, while instead this vector here, the vector 0, 1, stays the same, so it goes to 0, 1. So you have the matrix of transformation D, the Galilean matrix, because this is the Galilean transformation, which is 1 minus tangent of alpha 1, 0. Sorry, 0, 1. The tangent of alpha is called velocity and it is indicated as v, so v is the tangent of alpha. So the transformation here can be written like this. This is in matrix notation, which is equivalent to this: t prime equals t and x prime equals minus tan of alpha, so minus v t plus x. So this is the linear approximation of the transformation between t and t prime, and it is valid when t prime is a straight line according to t. Also notice that all linear systems are sent to linear systems with a linear transformation, so these linear systems form a class of systems which is called inertial frames of reference. The importance of inertial frames of reference is maintained also in our Einsteinian spacetime, but with something more, because with our Einsteinian spacetime, a straight line represents, in a flat spacetime, it represents an axis where a direction where the flux of information is kept constant. So all the straight lines in a flat spacetime are the path where the flux of information is constant, and you can easily look at that by drawing the clock. So as we said before, the pillars of Einstein's spacetime are the photons, while instead in Newton's spacetime the pillars are these abstract lines, but you can also see these abstract lines as the definition of the photon in Newton's spacetime. So in Einstein's spacetime we have, by our drawing convention, we have this grid of photons, this directed grid of photons, and with this grid we have this notation for the time axis, which is a simple way of writing this structure, which follows this grid. Instead, in Einstein's spacetime, everything is more abstract because you have parallel photons. Then the time axis is not equivalent to a connection of photons, because the photons here are all parallel and they can only travel left or right. Well, actually remember that these lines are a whole space, so actually they can travel all the directions in a space, but they don't travel in the time direction. But we are physicists, so we are aware that our theories are always approximations. In fact, we can see this as an approximation of this with the line. Let's say that the lines are not actually parallel but almost parallel, but actually they allow to connect the time coordinates through this grid, which is like this grid but very, very flat. Then the time axis has the same meaning as this. The only thing is that these segments are very, very flattened. So basically this angle here tends to 0 and this angle here tends to pi half 90 degrees. And remember that we called this angle velocity. So the velocity of the photon, which is indicated as c, here it is 1, or a number not very far from 1. Here instead it is the tangent of pi half. And the tangent of pi half is infinite. So we can see this as an approximation of this, where the angle tends to pi half to 90 degrees, so the velocity of the photon tends to infinity. In fact, Newton's physics arises from an approximation of Einstein's physics where the light has infinite velocity. So you can see that Einstein's spacetime can be seen as a generalization. It can emerge as a generalization of Newton's spacetime when we do these considerations about measurements and signal propagation. So we look at this and we look at the meaning of the time direction. We want a concrete meaning of the time direction. So all we do is make this line connected also to the time direction, and we arrive at this structure. Just here we have a unit of measurement of time which is more similar to space, while here instead our time units was very different from the unit of space, so we couldn't see this structure. And measurement is the most fundamental topic in physics, and reasoning about measurement, what it means to take measurements, what it means to propagate a signal. It's reasoning about these things that we arrive to the more concrete theory of Einstein's relativity. So our spacetime is made of these grid of photons with these squares. The squares are the units of the grid of photons, and the information goes in these directions. So the net flux of information is on this direction, which is called the time direction. And you see that in fact the components of information to the left and to the right get cancelled out, while instead the components on the vertical direction sum up. So information is accumulated in this direction. So while for the time direction you follow the direction of accumulation of information, for the space direction you follow the direction where information is cancelled. So you have this direction where there is no accumulation of information, and with our drawing convention it appears perpendicular to the time direction. So you have here the time direction and here the space direction, and although they don't represent an actual length because information is not accumulated, you can still label them. You add numbers, so you label them, and you can still put numbers on the space direction. In fact, coordinates are simply labels, independently on the concrete meaning of the labels. So let's do it here. You start from this point, you follow this, and you get the first second. Then you follow this, you get the second second, and so on. If instead you follow this, you get the first second in space, and here the first second in space. So you can associate to the space axis a pseudo length, which is not an actual length, but it would be the actual length if the flow of information was directed horizontally. And you can represent this pseudo length, for example, with an imaginary number, just to differentiate it from the length on the time axis. For example, here it is length I, here length 2i, 3i, and so on. So when you square the length, you obtain a negative number, and this is only a convention, but we see that it has also a mathematical meaning behind it. So this space direction is called the present, and notice that while in Newton's spacetime the present is all connected, here it is not. In fact, this event is connected by the photon path, but the photon path which arrived here are the events here, inside this region of the cone. So we never have information about the present. We only have information about the past. And also we can't send information to the present, but only to the future cone. So we went from a grid of photons to a grid of coordinates, and we constructed this grid basically by taking the ends of our clock with a fixed position in the space coordinate. And remember that our clock is a hypercylinder in 4D spacetime, so it can be represented as a cylinder in 3D spacetime. And by continuity you can project equivalent clocks. So this is a concrete visualization of this grid, where these are the clocks and the ends of the clock correspond to a point in space, a full circle in 2D space, and it will be a sphere in 3D space. Now we want to represent here our clock T prime, but as we said, we don't know yet the width of the clock, so the radius of this cylinder T prime. So we draw here our clock T prime, and what are the squares of light, the grid for T prime in the frame of reference of T? There will be something like this, right? You follow the path of light, and they will be something like this. So they will have this shape here, there will be these rectangles. So you follow the flow of information and you get the time axis T prime. The x prime axis, you get it by reversing the flow of information. So by our drawing convention, obviously, if we have drawn these in T, these light rays in T at 45 degrees, obviously the x prime axis will also be rotated of the same angle of the T prime axis. So if this is T, this is x, the T prime axis is rotated by alpha, then the x prime axis here is also rotated by alpha. So we can now draw here the x prime axis. So the space coordinate for the clock T prime. Now I zoomed the grid for 1 square, and if this is 1, 0, if this point here is 1, 0, where is it projected in the system of T prime? We don't need to draw the system of T prime, because remember that the flow of information is defined by the direction. So to know the time component of this event according to T prime, it's enough to draw the parallel to the x prime axis. So it will be here, and let's say it will have coordinates A, B. So this is A, and instead for the coordinate B we draw projection parallel to the axis T prime, so this will be B. It's analog by symmetry for 0, 1. 0, 1 will be instead in B, A. So our matrix of transformation, the Lorentz matrix, will be A, B, B, A. So the length of the clock T is projected to A here. Now remember, this is not the width of the clock of T prime, this is just the width of the clock T in the frame of reference of T prime. To find the width of the clock T prime, we do this reasonment. If we, by symmetry, the scaling of the length is always A. So if we project if we construct a clock like this in t prime and we project it back to the frame t, then this will be a squared. So this is 1 and this is a squared. So we can see with, if we use a ruler, we could see where 1 over a is, and it will be, let's say it will be around here. And we know that 1 over a scales array, so 1 over a times a is 1. So when we project it to S prime, it will have length 1 in t prime. So this is the clock of t prime because it's measured of length 1 in t prime. So we now can construct the clock of t prime as seen from t, and it will go like this. So it indeed ticks more slowly. Basically what we did is we sent these squares to these squares for one clock, and the squares maintained the area. This is necessary for the equivalence of the two transformations. So the determinant of this matrix, which represents the scaling of the area, must be 1. So we have b squared minus a squared equals 1. If it was not 1, then the inverse transformation would have determinant 1 over L, which would be different from the determinant L of the not inverse transformation. So the two transformations won't be equivalent. Now this equation can be written in parametric form with parameter theta as b equals sine, hyperbolic sine of theta, and a equals hyperbolic sine of hyperbolic cosine of theta. Actually the sign is not determined. By convention we write it b equals minus sine of theta, just because in the transformation we see that b here is negative. So the picture looks more intuitive. Often instead using the hyperbolic functions, this matrix is written with this gamma and this beta. Gamma is defined as the hyperbolic cosine of theta. So they have this relation by which we can write gamma as 1 divided by square root of 1 minus beta squared. So we can write all the transformation as a function of beta instead of the angle theta. And also, my mistake, I had reversed a with b in the determinant formula. Obviously the determinant here is a squared minus b squared equals 1. So these are the transformations, here written in terms of beta and here written in terms of theta. So while the Galilean transformation was a shift only in the space direction, so a shift only of the time axis, here the transformation is a hyperbolic rotation, which is symmetric with respect to the diagonal which represents the path of light. So we have the symmetry here between space and time. So here space and time are treated equally. So we have here that A is the hyperbolic cosine of theta, which is often denoted as gamma, which is the dilation factor. Now we can refer to beta as the velocity of t prime with respect to t, because to measure the velocity of t prime we take all the path of t prime, so all the points in which x prime is 0, because when the system t prime measures position 0, if we put it here we see that it represents in the system t the line x equals beta t, and since they are linear relations, we also have delta x equals beta delta t. So beta is the velocity delta x divided by delta t. And if we put this result here by using this relation, we get the time dilation formula. Delta t prime equals delta t divided by gamma. And remembering that gamma being the hyperbolic cosine of being b squared plus 1 is always greater than 1, we have that this is a contraction. So this represents the time dilation because we are now in the system of the clock t prime, the line where x prime equals 0. So if we express delta t, and t is moving with respect to t prime, we have delta t equals gamma delta t prime. So the time in the moving clock is dilated by a factor gamma. Now we are considering units where c, the speed of light, equals 1. So where the path of the photon is at 45 degrees from t and from x. But if you want to use a different unit for the speed of light, you simply say that this is the axis ct, then it's drawn the same, and then in the formula you simply replace t and t prime with ct and ct prime. So we will get, for example, that in general b equals b divided by c, if we are using units in which c is different from 1. And these transformations you multiply by c here, which is like dividing by c here. So we will have beta divided by c, which is v divided by c squared. And here instead we will have beta times c, which is v. So these are the transformations written in the new units in which c may be different from 1. And we see that the scaling of the x prime axis in particular is like the Galilean transformation, but with this dilation factor. So we finally have the new colors. So here is a quick review. Now I hope you can see the blue color, but it is simple because the blue color is the system t prime x prime, the red color the system t second x second. The red system moves to the left, the blue system to the right, and here are the transformations. The only difference is that here the angle is negative in the red system, so you have a minus sign in the x coordinate of p second, where p prime and p second are the points taken respectively where x prime and x second are 0. So they are taken on the time axis of the blue system and the red system. Now, taking the time axis of a system means taking the trajectory of the system. And when we take the trajectory of the system, the x value measured by that system of itself obviously is 0. And we define the proper time of a particle as the time measured by that particle, so as the time measured by the system where x is always 0. So we have notated here t prime equals tau and t second equals tau, and here are the projections of the points p prime and p second on t. We can now draw the level cos where every clock measures the same distance tau from the origin. So we have x squared minus t squared equals minus tau squared. So this is the equation of a hyperbola. So these level curves are hyperbola. So for example, if I take distance 1, I take the red hyperbola, the red hyperbolas. There are two hyperbolas. And if I take one for the distance and one for the pseudo distance, and if I take the blue hyperbola, it's the hyperbola where the distance is 2. Now the actual distance is not defined as tau, but it is defined as x squared minus t squared, so the square distance is minus tau squared. So we have that inside the cone of light where t is greater than x, the squared distance is negative, while instead outside the cone of light the squared distance is positive. In the light path where x equals t, the distance is 0. So the red curves are the points where x squared is 1, the blue curves are the points where x squared is 4, and so on. Remembering that we are in 4 dimensions, we actually have also the other projections, t with y and t with z. But if we assume that we have motion only along the x direction, then in these projections the t-axis coincide. So we have y equals y prime equals y second, z equals z prime equals z second. So the axes y and z remain unchanged, and we have the 4D Lorentz matrix, which is the 2D Lorentz matrix plus the identity matrix, because the vector 0, 0, 1, 0, so the y vector does not change it, and so does not the z vector. Also in 3D representation of spacetime, we have this kind of transformation between the cubes. If these are the x, t, and y coordinates, only the y coordinate remain in the same direction, while instead the t and x coordinate are transformed like this, and we have this transformation between the cubes of t and the cubes of t prime viewed in t. So this is the 4-dimensional definition of metric, and the level spaces are hyperboloids. So in 3D representation, the level surfaces are hyperboloids, and the hyperboloids is drawn like this. Of course, these are the cones of light, then the hyperbola. These are the hyperbola in 2 dimensions, and you draw here the cone of light also. So you will have here a surface which has here a hyperbola in all 360 degrees, and the same thing here. So in 3D representation, it's easier to visualize the geometry than in 2D representation, and we have that the surfaces, the part of the surface outside the cone where s squared is greater than 0, are hyperbola, which are rotated through the circles of 360 degrees. So it's a whole hyperbola of rotation. This is a hyperbola, and the borders are circles, the circles of the light cone, and the surface is therefore all connected. While instead the surface inside the cone, where s squared is less than 0, is disconnected. It's made of 2 surfaces. One is here. The borders are always the circles of the cone of light, and the pit is made of a hyperbola. So they are something like this. This is a hyperbola, and this is the circle. In the last part of today's lecture, we are going to formulate a useful language for our geometry. The geometric objects we are going to define are all independent on coordinate systems. First, let's define a vector. A vector, AB, is an oriented segment from A to B, so it's an arrow from A to B, and this is a very intuitive definition of vector. We notate it as E minus A to emphasize that it does not matter how we take it in spacetime, if we take it here or there, but only the direction and the length matter. So, for example, if this is C and this is D in another position of spacetime but with the same direction and length of AB, So for example, D is B plus P and C is A plus P, then we have that D minus C is B plus P minus A plus P. The P cancels out and this is still equal to B minus A. So this notation with the minus operation is very useful for vectors. So a vector is some length in a direction, and this is a very useful definition in flat spacetime because the direction in flat spacetime has a very straightforward meaning, which is, as we already said, the flow of information. So the direction in flat spacetime defines a precise flow of information. So if you take any point in spacetime O, the neighborhood of that point can be approximated as a flat spacetime, and that flat spacetime has a structure of a vector space with the hyperbolic metric. So you can do linear algebra on that neighborhood of the point. Now we define a parameterized line simply as a line P with parameter lambda, where lambda defines the position on that line. For example, here is lambda equals 0, here lambda equals 0.5, and so on. Here it can be lambda equals 1, and this is a parameterized line. A segment can also be parameterized. For example, this segment AB can be parameterized as A is the point, plus lambda times the vector B minus A, which means you take the position A and the segment is a settled point from A to B. So for example, if lambda is between 0 and 1, with this definition you have all the points between A and B, because when lambda is 0 this is A and lambda is 1 it is B, and when lambda is in between 0 and 1 you have a point in between A and B. Now conventionally in segments you take equals differences of lambda as equals distances on the vector, where the distance can be the distance S, the spacetime distance, that in flat geometry is equivalent in a vector in a straight segment as the distance on the paper. So if you take the R half, you have this is A plus 0.5 B minus A, and so on. So the parameterization of a segment in this way is very clear and intuitive. So these are the possible notations for a vector from A to B: AB with the arrow, AB without the arrow, VAB, B minus A, and this is the definition of segment as a parameterized straight line, that portion of the parameterized straight line between A and B. Now when instead of a parameterized segment you have a parameterized curved line, there is not a clear connection between the Euclidean length on the paper and the spacetime length. So if you take a parameterization of equal distances of Euclidean length on the paper, it does not have a clear meaning, a definite meaning on a spacetime diagram. Instead you usually should take as parameter the proper time, which in a curved line corresponds to different Euclidean length on the paper. And remember that if the cone of light is like this, then the more it is the more the inclination is close to the inclination of the cone, the more the Euclidean length of the paper is larger for equal spacetime length. So with this parameterization of proper time you have 1, 2 and 3 is far here, and you have this kind of parameterization. In straight segments there is no difference in using the Euclidean length on the paper and the spacetime length, because in a straight segment the flux of information is the same in flat spacetime. So there is a linear relation between the length on the paper and the spacetime length. For example, with the length of the paper it could be 1, 2. Here with the proper time could be 4, 8, but the relation is linear. When you have curved lines which don't have a constant inclination, it is useful to define a tangent vector, and the tangent vector in a point of the line gives the inclination of the line at that point. To approximate the line around A, which is P of tau 0, you take the Taylor expansion, and this is the difference, the infinitesimal difference, and the difference can always be written like this, and when the difference is infinitesimal, these nonlinear terms cancel out, and so in the linear approximation you have AB, the tangent vector, which is this derivative here. So for example, for a parameterized word line of a particle x is this word line, the velocity, the forward velocity of the particle is defined as the derivative of x with respect to the proper time of the particle. So that is the four-dimensional velocity, because if you define velocity with a time measured by a particular frame of reference, then it is something which changes in every frame of reference. Instead, for a universal velocity, you need to define it with the proper time of the particle. So the velocity in spacetime is very simple, which is the tangent vector on the trajectory of the particle. Writing a vector in Lorentz components, where x0 is the time, we call it a 0 to emphasize the spatial nature of time, and t by the time dilation is gamma times the proper time. Then the velocity vector can be written in Lorentz components like this. U0 is dx0 on d tau, which is dt on d tau, and it is gamma. And the spatial components of u are denoted as ui, because remember from the last lecture that Latin letters denote the numbers, the spatial components, so the numbers 1, 2, 3. Instead, the Greek letters are for the numbers 0, 1, 2, 3. So when we want to include the number 0, the time component, we use Greek letters. When we want to refer to the spatial components, we use the Latin letters, and they are gamma times the Newtonian velocity, we could say, which is dxi on dt. So we can write the velocity, the forward velocity vector, like this. Remembering the definition of the length of a vector, x1 squared plus x2 squared plus x3 squared minus x0 squared, we can calculate the length of the velocity vector, and for any particle it is -1. Remembering that beta is the modulus of the velocity, and that gamma squared, so is the hyperbolic relation gamma squared equals 1 divided by 1 minus beta squared. So all velocity vectors have length -1, and this independently of the coordinate system. We couldn't have such a relation for the velocity in Newtonian physics, because in Newtonian physics you only have the three components, the three spatial components of velocity, which can be arbitrarily big, and you cannot find a relation between them which is independent on the frame of reference. So we recovered the geometric nature of velocity, which was hidden in the fourth dimension. Remembering that length is a geometric property which is independent on the Lorentz frame in which it is calculated, instead of taking an arbitrary frame where x is t and xi, and you have to calculate the derivative with respect to tau, and it gives you gamma times 1 bi, and then you have to calculate the length of u squared like this. You choose the frame of reference of the particle, because there x is tau 0. Then it is very easy to calculate, to take the derivative with respect to the proper time, which gives you the vector 1, 0. 0 is a 0 vector, and so the length is straightforwardly -1. So choosing the right frame of reference is often useful to simplify calculations. But let's not confuse the length with the square length. So we had associated a clock length and a pseudo length. When the squared length is less than 0, it is a clock length. When the squared length is greater than 0, it is a pseudo length. Well, instead, if you take the square root from the square length, you get the length. And the clock length is an imaginary positive number because it's the square root of, it's defined as a positive square root of a negative number. Or instead, the pseudo length is a positive real number because it's defined as a positive square root of a positive number. So this is basically the inverse of the convention we had proposed before, for which we had indicated the clock length with a real number and the pseudo length with an imaginary number, because we were counting the length with tau. If we use tau instead of s, the signs here are inverted, and so the clock length measured with tau is real and the pseudo length measured with tau is imaginary. So this is our new convention, measuring the length with s instead of the proper time, because you have to remember this, s is equivalent to the proper time but with a minus sign in the square, so you only invert the convention but the meaning is the same. Now, from a point of view of vector spaces, the length comes from the metric structure, and taking the length is part of a more general operation, which is the scalar product. The scalar product for a general vector geometry is defined simply as a general linear operation between two vectors. Each vector space is defined with its own scalar norm. So you can notate the operation of taking the scalar product between u and v with g. G is the symbol for the operator of the scalar product, and this is the extended notation, which is very long to write because you have to write all the possible combinations, the linear combinations between v and u, the components of v and u, and you have the metric notation, which is more compact. Here G is the metric matrix or the metric tensor, and this is always the matrix notation but extended. And then you have the more convenient index notation, which is this notation but in compact form with the Einstein's summation convention, where the repeated indices sum up. So this would be the sum in all the possible combination of alpha and beta. And alpha and beta, remember, they go from 0 to 4, 0, 1 to 3, sorry, from 0 to 3. Then the squared length is defined as the scalar product of u with itself. So it is g of u. Now I forgot to say that the scalar product is defined as a symmetric linear operation, which means that guv is equals to gvu, so you can invert the vectors and you get the same result. So you have a symmetric matrix representing the metric, and you can write the symmetric property in index notation as g alpha beta equals g beta alpha. Now in a curved spacetime, the metric tensor could change from point to point. So if you take two vectors in some point, in some position of spacetime, and the same two vectors in another position of spacetime, the scalar product could be different. While instead in a flat spacetime, where the directions have always the same meaning in all the spacetime, the structure is independent on the position of the points on spacetime. So the scalar product, which defines this linear structure, is the same in all the spacetime, and we call the tensor G in flat spacetime as the tensor eta. So eta is the metric tensor in flat spacetime. Now it is straightforward to calculate the matrix components of eta, because we know we have defined our length for the flat spacetime, which is minor u0 times u0 plus u1 times u1 plus u2 times u2 plus u3 times u3. So the components for the metric tensor are eta 0, 0 equals minus 1, eta 1, 1 equals 1, eta 2, 2 equals 1, eta 3, 3 equals 1. While instead all the other components must be 0. So this is eta 0, 1 plus 0, u 0, u 2, so this is eta 0, 2. For these components equals 0. For the remaining components are equal to 0. So the matrix representation for eta is minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So it is a diagonal matrix. So now it comes why it is useful to differentiate between lower and upper indices in our notation. Because we can write the scalar product like this. This is the definition of the scalar product, but often it is more convenient to write it simply with the vectors u and b, and to do this you define this as u beta with, right, because alpha are dummy indices, they get summed over, and beta is a free index. You write it as u beta with the index in the low position. So you write the scalar product as u beta v beta. So with this notation, it is very important to differentiate between upper and lower indexes. Now in a Euclidean metric, you don't need to differentiate, because the metric tensor is the identity matrix. In Euclidean metric you don't have this minus 1, but you have 1 also here. So you will have u beta equals u beta, and it does not matter where the indices are, while instead here you have u0 equals minus u0, while instead for the partial components u1 equals u1, u2 equals u2, and so on, u3 equals u3. So like in Euclidean geometry, the partial components don't change, but this component changes because of this minus sign in the metric. Now to differentiate this from vectors, this is defined as a one form. So the one form is notated with the lower index. And vectors and one forms are related by the metric structure. So the general expression for the scalar product between u and v is this, which you can find with the matrix notation, or also with the one form vector notation, since u0 is minus u0 with the upper 0, and so on. So when you write the scalar product with all indices in the upper position, you have a minus sign on the first term, while instead in this notation, where the first term is not a vector but the respective one form, then you don't have minus signs. Now let's look at the geometric meaning of the scalar product. We have bilinearity as the product between u and v. Here we can take out the modulus of u and the modulus of v and multiply it by the unitary vectors in the directions of u and v. So if this is u, the unitary vector with this is where this is length 1. And so, since we already know the meaning of length in spacetime, we only are interested now in understanding the meaning of this product between the two unitary vectors. Now remembering that Lorentz transformations don't change the length of vectors, and they take the upper time-like vectors to upper time-like vectors, because remember that this surface defining the vectors with same length is separated in three separated surfaces. So this is the upper time-like surface, and lower time-like vectors are sent to lower time-like vectors. This is the lower time-like surface, and space-like vectors are sent to space-like vectors. And remember that the space-like surface is all connected, so there is no differentiation of lower and upper space-like surface or right and left space-like surface, but it is a whole space-like surface, and you can send with a Lorentz transformation a vector on this surface on any other point of this surface. So we have four cases. First, the trivial case where one of them is a light-like vector, then it has zero length, so the scalar product trivially is zero, so we don't have all unit vectors because one is of zero length and can't be a unit vector. But instead, considering unit vectors, we have these four cases left, where u and v are both upper time-like, when u is upper and v is lower time-like, when u is time-like and v is space-like, and u and v are space-like. So if they are both upper time-like, then we take the frame of u here. U is 1, 0, 0, 0. V is, here it is gamma, and here it is gamma beta, so gamma, and here it is gamma beta, but it does not matter because in the scalar product we only have 1 times gamma, so the scalar product is minus gamma. Symmetrically, if they are both lower time-like, then we will have here minus 1 and here minus gamma, so the scalar product will still be minus gamma. In the second case, where u is upper time-like and v is lower time-like, the frame of u is motion in the x direction. It is still 1, 0, 0, 0. This instead is minus gamma, gamma beta 0, 0. So the scalar product now is gamma. So when they are in the same cone, the scalar product is less than 0. As they are in different cones, the scalar product is greater than 0. Now if u is time-like and v is space-like, taking the frame of u with pseudo-motion of v in the x direction. Now this is a pseudo-motion because being v time-like, it does not represent a real particle. Then we differentiate v plus, v0 and v minus. V plus is a vector v with a positive time component, v0 with a zero time component, so it is in the x-axis, and v minus with a negative time component. Then we have u is 1, 0, 0, 0. This is gamma beta, gamma 0, 0. This is minus gamma beta, gamma 0, 0. This is 0, 1, 0, 0. So the scalar product between u and v plus is minus gamma beta, which is less than 0, and the scalar product between u and v minus is gamma beta, which is greater than 0. Instead, the scalar product between u and v0 is 0. When the scalar product between two non-zero vectors is 0, they are said to be perpendicular. So in a Lorentz frame, the time axis is perpendicular to the spatial axis. So when the vectors have both positive time components or both negative time components, the scalar product is negative, when instead where they have different sign in the time component, the scalar product is positive. Now if u and v are both space-like, we take the frame where u is 0, 1, 0, 0, which we can call x pseudo frame of u, and v is a generic space-like vector with the square length equals 1. We write v equals, here we have generic vx, vy, sorry, let's write v1, v2, v3 components, and here we will have the square root of L squared minus 1, where L squared is v1 squared plus v2 squared plus v3 squared, the Euclidean norm on the space components. This does not matter for the scalar product. The scalar product will be v1. So the scalar product between two space-like vectors can generically be less than 0, 0, or greater than 0. Now some notation. We notate vectors in one form with a bar, usually to distinguish them from the components, because yes, we denote the components with an upper index for the vectors, and we numerate vectors by using a lower index, but to differentiate them from the components of the one forms which also have a lower index, we write here also the bar. So for vectors, we numerate vectors with lower index and the component have the upper index. One forms we numerate them with the upper index and the components have the lower index. So in order not to make confusion between these two, we put a bar here and also we put a bar here. Then here we have the Lorentz space, which is usually denoted with 0, 1, 2, and 3, where 0 is the time-like vector and 0 orthogonal, and orthogonality can be expressed like this. I don't know if you know this symbol. It is the conical delta, which is 1 when alpha equals beta and 0 when alpha is different from beta. Instead, the Lorentz space for the one forms is simply the base made of the one forms, which are the corresponding one form with the vectors from the Lorentz space, and they are denoted with omega. For completeness, I also tell you this, that another common name for the scalar product is the dot product, because the dot notation, and also another notation for the scalar product is this, which is used very often. Although in this notation, this is usually considered the vector, and this is usually considered as a one form. So this should be the corresponding one form of the vector u. So given a basis one form and a basis vector, the bracket product is equivalent to the scalar product, which is delta alpha beta. Now it is independent of the position of the indices in the conical delta, but we want a correspondence with this notation, so we put alpha up and beta in the lower position. So you can see one forms as functions which take vectors as an argument and they give the bracket product as a result. So they give the scalar product with the equivalent vector of sigma. Although we have defined this expression with vectors sigma and u, and this expression with 1/4 sigma and vector u, we can write also this considering one form here, because one form sigma and its vector counterpart represent basically the same thing. In fact, the result of this is the same. So if we take here the vector corresponding to the one form sigma, it gives the same result as this. So we can use sigma as a vector in this notation and sigma as a one form in this notation also. The distinction is more a matter of convenience of notation, but often it is useful to write the scalar product between two one forms and the bracket product between two vectors. Now, remembering the summation convention, it is useful to write the vectors in component notation, the vectors and the one forms in component notation, and this is a representation for the one forms. So the type of basis vector is denoted with of basis form is denoted as an upper index. The component in that direction is denoted as a lower index, and it is the opposite for the vectors. So it is useful to study the metric structure in component notation. So we write the scalar product between sigma and the basis vector, the alpha, as by using this relation we write it as sigma alpha by the linearity of the scalar product omega alpha I have to use a different index not to be confused with this. So sigma beta, omega beta, and E alpha, and this is equal to sigma beta, these are the components, delta beta alpha. Since delta is equal to 1 only when alpha equals beta, this is sigma alpha. Likewise, we can write omega alpha, the scalar product between the basis one form omega alpha and the vector, the generic vector v, as v beta omega alpha e beta, and this is v beta times delta alpha beta, that is relation, and this is v alpha. In general, for a scalar product between a one form and a vector, we have writing it in component notation. For example, we can write sigma alpha in component as sigma in component as sigma alpha times omega alpha v, which gives this if this, which is v alpha, so this is omega sigma alpha v alpha. We can also find this result by writing v like this in component notation, of course. So this would give v alpha, we don't have a bar here, so here, so v alpha times sigma v alpha, and this is this, which is sigma alpha, so it is v alpha sigma alpha. So rewriting the result we obtained, we have that if we take the scalar product of sigma with the basis vector with the basis form omega alpha, we get the alpha component. So the projection of sigma on omega alpha, taking the vector product, taking the scalar product between v and the basis vector e alpha, we obtained the alpha, the alpha component of v, so the projection on e alpha, projection of v on e alpha. Conventionally, we have written this as this in vector form, remembering that omega alpha is the vector, is the one form corresponding to the vector e alpha, and also here conventionally we have written e alpha in one form, because conventionally this bracket product is usually written with a one form here and a vector here. Instead, for the scalar product between v and omega, we obtain v alpha omega alpha, which we can write by writing omega alpha with its vector equivalent as beta alpha beta times sigma beta. We have simply recovered the expression for the scalar product we already knew. So the geometric interpretation is like in Euclidean geometry, the projection. So the scalar product between v and u is the projection of v on u. So for example, if u is a unitary vector, if it is not unitary, you simply divide by the norm and then you add it later. We are interested now in the geometric interpretation of the scalar product, not in the norms, so it is not important if we take unitary. And we take it unitary because so we can have a frame of reference in which it is a basis vector. So now we know how projection works in Euclidean geometry, so we focus now on the time-space plane. So we represent the scalar product in the plane where we take 0 the basis vector, the basis time-like vector, and ei a generic basis space-like vector. So if u is, for example, a generic space-like vector in some frame of reference, in the case where it is the time-like basis vector is equivalent because you simply have to reflect through the diagonal, which is the light path. So without loss of generality, we consider the case where U is a space-like vector. So in this system, in this frame of reference, U is a basis space-like vector, U EI. Here instead it is not. Here it is a generic space-like vector, and the scalar product formula is this for a projection between B and a basis vector. So this is the scalar product B times U, and remembering that this is a scalar, it takes the same value, it is evaluated the same in every frame of reference, so also here it should be evaluated the same. So now is 0 prime, I have drawn the prime just to differentiate the two basis vectors here in this drawing, where E0 is the basis vector in this frame and E0 prime is the basis vector for the frame where U is EI prime. So drawing the projection here we must take the parallel to this vector, which is the equivalent of this vector. So we take this parallel and we project in U, and we should get, if I have drawn it well, we should get about the same result. So we should get here about the same length, the same paper length if I have drawn it well, and it is evaluated also as B times U. So this is a visual representation of the concept of projection in space-time. I mean the same length scaled with U, of course, because here U we have a paper length a bit larger than this. So also this piece here will be our paper length a bit larger. It must be the equal in proportion. So for example, if B times U is, so it can be about 6/5, 6 divided by 5. So we divide this vector in 5 parts, 1, 2, 3, 4, 5, 6. Then also here we divide this in 1, 2, 3, 4, 5 units of length. And here we have the 6 units of length, where the unit of length I have taken here is 1/5. So this was an introduction about the structure of flat spacetime, and now it should be clear what time is as a geometric concept. We have also talked about vectors and one-forms, so we have already differentiated the upper index notation with the lower index notation, and in the next lecture we will also introduce tensors, and there will be a lot of index notation in the following lectures. So see you next time.